Daniel, are you having trouble with graphs?
Yeah.
Graphs are used all around us, and you may not even know. There's user-to-user connections like on Facebook, or the bus route that connects your apartment to the rights union.
A graph consists of vertices and edges that connect some or all of the vertices. Let's break it down with an example. Say you're walking from a class to another class.
You start your walk at your first classroom. The first classroom is the first vertex. So Daniel, draw a dot right there. Yes, right there. A vertex is a point. It functions as an endpoint usually. So this also means the second vertex is your next classroom. Daniel, draw another dot. No, somewhere else.
Yes, there. Vertices can be connected by an edge. Edges can be directed or undirected. Edges are essentially the way you walk to your class.
Directed graphs have edges with directions, therefore beginning and end vertices. Daniel can start it here and end it here, or the other way around. Regardless, you know where you are going. You start in classroom A and take a specific direction to class B, right Daniel? Go ahead and draw the arrow.
But an undirected graph doesn't tell you the specific direction, and the edges are lines without direction. What? You simply know that to connect the two classrooms, you take this route, but are unaware which direction you're going. Erase the arrow, please. But what if Daniel forgot something in class A when he's on his way already to class B?
Then you're walking in a loop. You leave class A just to return to class A.
There are a few more terms that we should go over before digging in some more. Let's revisit an undirected graph. Degrees tell you how many times a vertex functions as the endpoint of edges. So say you're at a party.
And you're this guy. You show up to a person and say, "Hi, my name is Daniel."
How's it going? I'm Daniel.
Then shake his hand. That's one person you introduce yourself to. That's 1 degree. If you go to another one, that's degree 2.
Hey, how's it going?
Now, if Daniel is standing here to this guy and this other guy, he is adjacent to this guy. He can call them his neighbors. So then, I guess this is Daniel's neighborhood.
Okay, but I still don't understand this whole connectivity thing.
Well, first, there's paths. A simple way to look at a path is to start at one vertex and continue traveling around from vertex to vertex using edges. The path is said to traverse the edges and pass through the vertices.
Imagine if you wanted to go on a road trip. It would be useful to know which cities you'll be visiting in what order, as well as what roads you'll take to get there. In this case, the city is a vertex, and each road is an edge.
But with most road trips, you will probably want to start and end at the same place, normally your home. Daniel, connect the last point to the first point. When looking at graph theory, if the path you take starts and ends at the same vertex, we call that a circuit. We call it simple if it does not traverse the same edge twice, like what we have here. Now, there is another concept known as degrees of separation, and is defined as the number of steps it takes to get from one node to another. Daniel, pick a node. A node has 0 degrees of separation from itself, but its neighbor, Daniel, point to the one next to it, has 1 degree of separation from the node since it takes 1 step to get there. Visually, the number of degrees of separation is the number of edges connecting 2 vertices in a simple path. Fun fact, there is an idea called 6 degrees of separation, which states that all living things and everything else in the world are 6 or fewer steps away from each other, so that the chain of a friend statements can be made to connect any 2 people in the maximum of 6 steps.
Moving on, an undirected graph is called connected if there is a path between every pair of vertices. An undirected graph that is not connected is called disconnected. We say that we disconnect a graph when we remove vertices or edges or both to produce a disconnected subgraph. So go ahead and erase an edge.
Okay, but what about these directed graphs? Is it the same?
When it comes to directed graphs, there's a little more to it. There are two new types of connectivity we have to learn for directed graphs. The graph can be strongly connected, weakly connected, or again, not connected at all.
Let's pretend that instead of each directed edge being just that, it's a river with a current flowing a certain way. Now imagine you had a box, and when you set the box down, it flows in the same direction as the river. For the graph to be considered strongly connected, no matter what vertex you start at, the box must be able to make it to any of the other vertices using only the flow of the river.
If this is not the case, but the graph still is connected in the underlying undirected graph, then the graph is considered weakly connected.
The idea of connectedness can also be extended to the subgraphs of a graph. A connected component of a graph is a subgraph in which any two vertices are connected by paths. Every vertex of the graph lies in a connected component that consists of all the vertices that can be reached from that vertex, together with all the edges that join the vertices. In this example, there are three connected components. Now, seeing how the graphs can be connected, let's explore how we can disconnect connected graphs. Are you ready, Daniel? First, I will be talking about cut vertices and cut edges. A cut vertex, or articulation point, is a vertex that, if removed with its incident edges, produces a subgraph with more connected components than in the original graph. So Daniel, put an X over vertex C. This produces two connected components from the original one graph. On the second graph, place an X over edge B. This is a cut edge or bridge, meaning that if the edge is removed, it produces a subgraph with more connected components than in the original graph. Once again, we have two connected components. Go.
But not all graphs have cut vertices or cut edges, so we need to extend the concept. A vertex cut, also known as a separating set, it's different from a cut vertex, is a subset of the vertex set of the graph, such that if you take away those vertices and their incident edges in the subset, the resulting graph is disconnected. So Daniel, let's look at a vertex cut by taking away vertices C and D. The resulting graph is shown below. Now the vertex connectivity, denoted by kappa of G, is the minimum number of vertices in a vertex cut. In this case, the minimum number of vertices needed to be cut is 2. So kappa of graph G is 2. A graph is also known as k-connected if kappa of G is greater than or equal to k. So in this example, the graph can be called 1 connected or 2 connected. Similarly, an edge cut is a subset of the graph's edge set, such that if you take away those edges, the resulting graph is disconnected. So Daniel, take away the edges between C and D and C and F. The resulting disconnected graph is below. Also, edge connectivity, denoted by gamma of G, is the minimum number of edges in an edge cut. So in this case, gamma of graph G is also 2.